We are actually trying to ask simpler questions so that we can answer it. Now suppose if I ask what is 2 power I, that is, now I kept power as I, base as a real number, 2 power. Is it real or imaginary? Is it a complex number or a real number? Or what are the real parts of this? Real part of this number. Suppose if that is 2 power I. Our ultimate aim is to ask a question: what are the real and imaginary parts of some Z1 power Z2? Where Z1 is also a complex number, Z2 is also a complex number. That is what this is. Correct? So, if 2 power I, is it real or imaginary? Let me tell you one more trick. Suppose Z is equal to 2 power I. What will be Z star? 2 power minus. Correct? Now Z plus Z star by 2. What will that be equal to? 2 power I plus 1 by 2 power I divided by 2. Correct? So that is equal to 2 power I into 2 power I, which is 2 power 2I plus 1 by 2 power I. So that is equal to 2 power I. So ask what is logarithm of Z. That is I logarithm of okay? I logarithm of. So if you have Z is equal to x plus I which is e to the power r into I theta, when you take logarithm of Z, you have logarithm of r plus I times theta. Correct? So what is the real part of logarithm of Z? Real part of logarithm of Z is logarithm of r. Imaginary part of logarithm of Z is theta. Correct? So in this case, real part of logarithm of Z is equal to 0. Imaginary part of logarithm of Z is equal to log. Okay, so that means if I compare this result, logarithm of r is equal to 0, this implies r is equal to 1. Correct? Imaginary part, that is theta, is equal to logarithm of 2. Logarithm of 2, correct? So that means, so what will be the real part of real part of 2 power I? Real part of 2 power I is equal to r cos theta. It is cos of logarithm of 2. Imaginary part of 2 to the I is sine of logarithm. So it will have both real and imaginary. Now first what happens if Z is equal to I to the power I. I to the power I. Is it what is the real part? So you write I as e power I by 2 to the power I, which is equal to e to the minus I by 2. So real part of I power I is e power minus 5 by 2. And imaginary part of I to the power I. So I power I is real number. Maybe it's not expected. So I to the power I is a real number. What about the actual problem? We started with this problem. Shall I leave? E to the power minus 5 by 2. I into I is minus 1, so e to the power minus 5. So shall I leave this problem for you to find out what are real and imaginary parts of I to the root I? And maybe some more problems like this you can do in the tutorial, just to get practice. So these are the tricks that we will have to practice for dealing with the complex. Now my second topic is compactification of this real complex plane. This is also called stereographic projection. As we have seen, the complex plane, every point in the complex plane can be represented as a point on the surface of a sphere. So the technique by which we accomplish this is called stereographic projection. You know, if you consider a sphere, and let's say this is your equatorial plane, and consider the complex plane is coinciding with this equatorial. This is your complex plane. That is, you have a sphere cut across the equator, then you have this complex plane. Let's say this is your north pole and this is your south pole. Now stereographic projection is defined in the following fashion. You draw a straight line from the north pole to a point on the plane. This will cut the surface at some point. Correct? You are drawing a straight line from north pole. This is north pole. This is south pole. So you draw a tangent. You draw a straight line from here to a point. So let us call this point as z is equal to x plus iy. This is any arbitrary point on the complex plane. Now this line will intersect the surface at some point. Okay. So let's say this is the center of the sphere. This is a unit sphere. So this is a unit sphere. That means radius is 1. So this is the center of the sphere. Okay. And this point is the representation of this complex number. What is that point? The point of intersection of the spherical surface and the straight line drawn from the north pole to a point of the complex plane. So this point is mapped on this point. So this is what is called theory of data. Now you can see that all points inside this circle of equatorial circle will be mapped onto the southern hemisphere. All points which are outside this equatorial circle will be mapped onto the northern hemisphere. Correct? Because if I draw a tangent like this, if it is cutting this equatorial circle, it will cut the surface in the southern hemisphere. If I have something outside this circle, that will cut this in the northern hemisphere. So all points within unit circle around the origin, okay, that is points such that modulus of z is less than 1. Modulus of z is less than 1 means within unit distance from the origin. Points with this are mapped to southern hemisphere. And points with mod z greater than so I can think this is less than equal to 1 here, greater than 1 are mapped to northern hemisphere. So what is the point to which origin mapped to? Just to make sure you are following what I am saying. What is the point? The origin is mapped to which point? South pole. Origin is mapped to south. So because you draw a line direct here, origin is mapped to south. Now you can say that if I have a point at infinity, suppose I have a point at infinity, what happens? It will go parallelly, right? So all points at infinity are mapped to n. Okay? So there, in this is why it is called compactification. The entire infinite plane, I compactly represent it as a sphere. That all points at infinity is only one point here. So you can say there is only one point at infinity. Okay, so all points of origin have to south. And all points at infinity are mapped up. Now you can write down in spherical polar coordinates, for example, if you want to call these coordinates as xi1, xi2, xi3, you want these coordinates as xi1, xi3. Now these coordinates can be related to this x and y. What is xi1 in terms of x, y, and what is xi2 in terms of that is what is called mapping, right? You know x, y, you should know what is this point. And in the spherical polar coordinates, xi1 is sine theta cos phi, where this theta and phi are colatitudes and azimuthal angles in the spherical polar coordinates. Xi2 is sine theta, sine phi, and phi3 is I have called it as a unit sphere, so the radius is 1. So I have these coordinates in terms of spherical polar coordinates. So spherical polar coordinates, you consider this as the 2 axis, this is the 1 axis, the 3 axis. This is 1, this is theta, and this projection is spherical polar coordinate. And as we know, the tri-1 square, the tri-2 square, the tri-3 square. The units Satya. Okay. So I can leave this as an exercise. You can do it in the tutorials. Relate just using the geometry. Right 1, right 2, right 3. This complete this now. So essentially, this sphere, what actually has all the information about the complete complex plane is called the Riemann sphere. So this mapping is what is called stereographic projection. This sphere is called Riemann sphere. So, if Z the complex variable defined as x plus I y r e power I theta r e power I theta. You can use any of these notations. Then you define f of z as a function of complex variable. That means essentially for every complex number z, there will be another complex number. So this is essentially a mapping from complex plane to complex. So you can say that this f of z will be written as u of z plus I times v of z. So you have a complex plane where this is x and this is y. You have another complex plane where this is u and this is v. So a point z here is mapped to the point f of z. This is the meaning of saying we have a function of the complex. But u also depends on z, v also depends on z. And z is in itself two independent real variables. We can define all those things that we know in real analysis. We can define limits, we can define continuity, we can define derivatives in much the same way, except we have to keep in mind that here the limit, continuity, etc. will involve all directions in which you approach that point. Okay. So, if you want a function f of z to be continuous at z naught, then limits that you approach from any direction in Z naught should give you same limit and it should be equal to the value of the function at Z naught. So in such cases, we can define continuity, differentiability, all those things in a similar way that we have defined here. Among this, there is one important class of functions. They are called analytic functions. A function f of z is analytic if analytic at the point z equal to let's say some z naught, if f of z is differentiable at z equal to z naught and also at every point in some neighborhood of z. Essentially what it means is that if you have a complex plane and this is a point z naught, then you must be able to have some region. It should not be that point alone. This region can be very small, but there should be some region in which f of z is differentiable not only at this point but also at every point inside that region. So it is required that there should be a neighborhood in which this point is differentiable. This function is differentiable at all points in some neighborhood. Now, if you consider f of z is analytic at all points, analytic in C, at all points in C, then we call this f of z an entire function. So entire function means it is analytic everywhere. That this derivative exists at all points. The entire function means that it is analytic everywhere. Okay, so any questions? Yeah, so for example, f of z equal to z star, not an analytic. And I am just going to say that if you have a function which depends on z star, it is not analytic. Z star is not analytic. Any function which has a dependence on z star is also not analytic. In fact, df by dz star is equal to 0 is the necessary condition for derivative. Rho f by dou z. Rho f by dou z star is equal to 0 is necessary for the function to be analyzed. If the function depends on z star, it's not analyzed. You all may be familiar with conditions called Cauchy-Riemann conditions. Cauchy-Riemann conditions are necessary for the function to be analyzed, correct? And you can derive Cauchy-Riemann conditions from this. This is equivalent to Cauchy-Riemann conditions. Sometimes it is very useful to check this condition than writing Cauchy-Riemann condition. Any other questions?
If your function is said to be continuous, can we say that it is analytic?
No. Continuity does not even mean it can be differentiable. But analyticity requires it is differentiable at that point and also at some point in some neighborhood of that. So continuity does not even guarantee differentiability. Even if that is true in the real functions of real variable also. For example, take mod x. Mod x is continuous at R0, but it is not differentiable. So continuity is a necessary condition for differentiability, but it's not sufficient. Same way, continuity doesn't imply even differentiability. So you cannot publish this it is arbitrary. It can be any small epsilon neighborhood, epsilon can be any small. So some neighborhoods exist, but there is no restriction on how much to be given. So maybe we can just I can also ask you to try this, but we can do it in the tutorials if you are not able to do. So from here, then Cauchy-Riemann. You have to use what is called some chain rule for the differentiation. You know that x is nothing but z plus z star by 2, y is nothing but z minus z star by 2i, and then dou u by dou x, which is their Cauchy-Riemann conditions, you can write them in terms of z star. So if you have, just to complete, if you have f of xy as u of xy, d of I times d of xy, Cauchy-Riemann conditions will give you dou u by dou y is equal to dou v by dou x, and dou u by dou x not know if this minus sign is here or here. These are called Cauchy-Riemann conditions. Right. This implies there was a where they have a function with a parameter called a. Now they are asking a question, for what value of a this function is analytic. Usually they will give multiple choice questions in entrance exams, right? So what value of a is this analytic? Now in those choices there are some real numbers and some complex numbers also. So I cannot use this if I want to, because I don't know, unless I fix A, I cannot find out what is the real part and what is the imaginary. I am telling the case where it becomes difficult to use this. So unless I fix A, I do not know, because A, suppose A is I. One choice is A is I. If I put A is equal to I, my U and V will be different. If I put A is equal to 1, my U and V will be different. So I do not know beforehand which one I should take. Otherwise I have to take each choice and put it and then verify. But if I use this, then I can rearrange, put wherever x is there, z plus z star by 2, wherever y is there, put z minus z star by 2. And if the equation becomes independent of z star, that means it is analytic. For what value of a, the equation becomes independent of z star. You ask that question, then it will be so that you will get the value of a. But to find out u and v, you have to put the value of a. Do you understand the difference? So this is very useful in that case where you don't have to put it, but you demand this, you will get the value. Okay, maybe I will just define give two definitions and then we will stop that. A region in the complex plane, suppose I have a complex plane and there is some region. This region is called simply connected. This region is called simply connected. If I, so this region we will call it as, let's say, some R, some region R. If I draw a open, if I draw a closed contour inside this region, the region enclosed within the contour should belong to this region. Wherever I can draw any closed curve inside this region, and the region inside the contour that I am drawing should be the part of this R. Then it is called simply connected. For example, I take a region like this, where I have this annular region. This region I don't have. I have only R is the annular region. Okay. Now if I draw a contour like this is a closed curve in R, but inside the curve I have some region which is not in R. Such regions are called multiply connected. This is simply connected, this is multiply connected. So these two notions are important for us to develop Cauchy's integral theorem and Cauchy's integral formula. So just defining, this is called simply connected. Is any closed contour in R contains here this is called multiply connected. is Cauchy-Riemann condition. So you can get Cauchy-Riemann conditions by asking this question: f of z plus delta z minus f of z divided by delta z, and take this limit delta z to 0, and then you write f of z as f of xy is equal to u of xy plus I times v of xy, and in the complex plane if you have z, any arbitrary z, you can go to this z from any direction. So one direction is from this point, let's say this is your delta z, you can go to this limit in this way. That is, first make delta x going to 0 and then make delta y going to 0, or you can go this way. That is, first make delta y going to 0 and then delta x going to 0. So you try to take two paths, path 1 and path 2. In one path you execute this limit, and in another path you execute this limit, you should get the same answer if the derivative at this point exists. Correct? So you can write this quantity as limit u of x plus delta x comma y plus delta y plus I times d of x plus delta x comma y plus delta y. This is f of z plus delta z minus u of xy minus I times b of xy. This is f of z divided by